Hi children, hi students, that is welcome back to physics class, that is your favorite channel Physics by Imagination. So dear children, and in this class we are going to understand about moving charges and magnetism too. So I had explained in part 1 about magnetic force, Lorentz force, okay, and we discussed about those topics. So we'll discuss remaining topics, that is today we'll understand about straight wire, circular loop, solenoid, toroid, force and a current carrying conductor kept in the magnetic field. All it is due to magnetic field. So let us learn without wasting time. So we know that according to Oersted effect, consider a wire and if it carries current, so surround this, it is going to produce what children? Magnetic field. That is, whenever current carrying conductor, okay, produces magnetic field around the current. So this I will consider at point P, and here I am going to consider current element, that is dl. According to Biot-Savart law, it is a small portion area to find the amount of magnetic field. Now in this direction we could find the magnetic field. So dear children, it is very easy to understand that. So what happens here? It's very simple. So now here the current is moving. So now current is moving means what is going to happen? Very simple, that current is moving in this direction, magnetic field is present around this. Okay, so what is going to happen here? So now here we want to find this magnetic field. Now we know that according to Ampere Circuit Law, Ampere Circuit Law, ACL, Ampere Circuit Law, we can written as, that is integration of mu naught, that is integration of magnetic field, integration of line integral, that is B dot dl is equal to mu naught times of I. Now here this is nothing but the amount of magnetic field that is directly proportional to I, means the line integral of the magnetic field in a closed circuit, that is which is equal to net times of the amount of current enclosed by the surface. Means if current is increasing more, means magnetic field will be increased more, that's it. So this magnetic field totally depends upon current, and mu naught is called what? Permittivity of free space, that is equal to 4 pi into 10 to the power of minus 7, we will use in the numerical spot. Now here, so here if I want to find this magnetic field, I'll take constant, so it becomes dl is equal to mu naught times of I. The children, here we are going to also consider cos theta. If theta is very small, we are going to take directly, that is line integral, integration of B dot dl. So now here dl is nothing but area of element, so that we have considered, that is circular loop. Then area is nothing but circumference. So what is circumference? That is, we'll take dl as 2 pi r, means the length of the circle of the wire. So then it becomes 2 pi r is equal to mu naught times of I, and b is equal to mu naught I divided by 2 pi r. So this is the expression for magnetic field due to current carrying conductor, just wire. Now by this equation, what we can analysis? This amount of magnetic field is directly proportional to the current. If current increases, the amount of magnetic field will be increased. If current decreases, amount of magnetic field will be decreased. Increased means increased, decreased means decreased. And inversely proportional to radius. If radius is decreases, the amount of magnetic field will increases. If radius increases, means the amount of magnetic field will decrease. Please note down this formula. So after this we will go for circular loop. Very, very important children. So now here we have considered a wire, a just wire. Now we are going to consider a loop. So we are going to consider a loop which is covered with a number of turns and connected to. So this is all we will understand by using Fleming's left hand rule. Means when our current carrying conductor, we hold the three fingers mutually perpendicular to each other, then this is indicating that motion of the conductor, this is magnetic field, this is direction of the current. Now here in the previous case I have produced a less amount of magnetic field. Now here I am going to produce more amount of magnetic field. Obviously will feed more amount of magnetic field. Now this I'll consider after passing current around this wire, we can find a magnetic Q. Okay, we can find that there is a presence of magnetic field. So that I'll change the diagram. This is a loop, I'll take a circular loop. This is O origin. I've taken, means here we have coated with number of copper turns. Now I'm going to take point at P, and this magnetic field here is going to find, and here I am going to take two components, horizontal components as well as vertical components. So this is y-axis, this is x-axis, and here I am going to take a area of element, that is small portion, to find the amount of magnetic field. Now I am going to join this line because surrounding this there is a presence of magnetic field, and this is alpha, and this alpha is nothing but, children, angle between the horizontal axis x and direction of the magnetic field, alpha. So now here directly we can get the expression. So this is about a circular loop, the magnetic field due to current carrying along the axis of the circular loop here. Okay, now this is distance from origin to the magnetic field, how much magnetic field it is going to be covered. So if it covers less, means distance will, magnetic field will increase. Now this is a radius. So directly we can write, children, the derivation part is very lengthy, but see it, this is a crash course. So I'll take directly expression as, that is amount of magnetic field in this circular loop is given by, that is mu naught times of I divided by 4 pi 2 pi n I r square divided by r square plus x square all to the power of 3 by 2. 2 pi n I r square divided by r square plus x square all to the power of 3 by 2. Here let us understand, n means what, children? Number of turns per unit length. So directly we will ask in the exam, that is directly we will ask the formula, that is n is nothing but number of turns per unit length. Remember this, number of turns per unit length. I means amount of current passing through this circular loop. R means radius, and this is r square plus x square to the power of 3 by 2. Here we will find two cases, children. What is the first case? The first case is very simple. The magnetic field due to at circular loop, then distance will be neglected. So it becomes mu naught by 4 pi. Okay, mu naught by 4 pi. So 2 pi into, I'll take a single wire, that is I r square, and this is going to be neglected. It becomes r square to the power of 3. Okay, by 2. Now what is going to happen, children? 2 cancelled. So we'll get mu naught by 4 pi, that is pi cancelled, 2 1 ja, 2 2 ja. Here we'll get, that is r square I divided by r cube. R square cancelled here, it becomes mu naught divided by 4 pi into, that is I divided by r. So this is 2 times is there. So this is the mu naught times of I divided by 2 pi r. This is the magnetic field due to at the center of the circular coiling loop, or the magnetic field due to at the center of the circular loop. Okay, mu naught times of I divided by 2 pi r. And also it is inversely proportional to what, children? That is radius. Okay, so please note down this formula. So later on, for this whole coil, that is depend upon n number of turns. If that is mu naught I n divided by 2 pi r. N means what, children? Number of turns. I have taken for single loop, that is mu naught I divided by 2 pi r. If I take a number of turns, means that is going to become B is equal to mu naught n I divided by 2 pi r. Please note down. So after this, without wasting time, let us understand that is magnetic field due to a solenoid. So what is solenoid, children? That is an insulator. So this is solenoid, third point. So it is an insulator, children. Now we have totally coated with large number of copper tons and connected to battery through plug key. Now here definitely it is going to produce more amount of magnetic field. There is no doubt at all. Now it has produced a magnetic field around this. So from this is, in this way it is going to produce magnetic field. Dear children, this is called electromagnet. Means when we pass the current through this insulator and which is wounded with copper wire, it is going to produce uniform magnetic field. Means what is solenoid? It is an insulator coated with large number of turns and produces uniform magnetic field. That is called solenoid. Now here this is north and south. This is acting like a bar magnet. Means outside the magnet they are moving from north to south direction. Inside the magnet they are moving from south to north. Very important point, children. When the magnetic field lines are moving anti-clockwise direction, anti-clockwise means that is acting like a north pole. Clockwise means that is acting like a south pole. So this is called also dipole. It is called also dipole. Now what is my point, children? Very simple to explain you that. Here outside the magnetic field we have found that is the magnetic field lines, they will move from north to south, inside south to north. Very important point. Now these lines, do they intersect? No, children. These magnetic field lines will not intersect. It is as if what we are discussing in the bar magnet properties. Okay, so it is equivalent to bar magnet. So directly, children, we can take as expression for solenoid is given by, that is B is equal to mu naught times of Ni. It means what, children? This is dependent upon ion. So what is ion, children? Ion means very simple. Current, area of coil, number of turns. Means what we are going to produce, whether large amount of magnetic field or small amount of magnetic field in this solenoid, that depends upon amount of current passing in this solenoid and area of the conductor and number of turns in the coil. Okay, so it is used to find, very important for CET, that is magnetic field due to solenoid is given by mu naught times of Ni. N means number of turns per unit length. So we can written as that is N by L. So in the exam they will give number of turns per unit length. Very useful, please remember. Now due to toroid means, children, it is a circular loop which is coated by large number of copper tons. And also by here also we can find same formula. The amount of magnetic field in the circular coil, that is in the way of circular, it is going to produce what, children? That is magnetic field. That is given by B is equal to mu naught n times of I. So here inside the circular toroid, the magnetic field is 0 because there is absence of current. There is no charges are present. We discussed it. Inside the conductor, that is electric field is equal to 0. Okay, now this is equal to 0 and outside also it is equal to 0. Now here surrounding this we can find that is maximum amount of magnetic field. So this is all about magnetic field due to straight wire, circular loop, solenoid, toroid. So let us understand without wasting time, that is we are going to understand force on current carrying conductor kept in the magnetic field. Dear children, very important. So let us consider a aluminum piece wire. Okay, so we are understanding this point now. So we have kept in the uniform magnetic field. So now this is the piece of aluminum piece wire and it has length L, okay, and we are going to consider an angle theta, and here it is going to carry the current I. So current is moving in this direction. A simple diagram, and this is uniform magnetic field. This is uniform magnetic field. Means this conductor experiences a force, that is called force experienced by the conductor when it is kept in the magnetic field. Let us understand this. The children, we have kept in the magnetic field and it is current carrying conductor. According to motor rule, what it is telling? The current carrying conductor kept in the magnetic field which experiences a force. Because fan is going to be rotated, because copper wire is kept between magnetic field, it is going to get mechanical force, rotational motion. Now this force is given by, so we know that magnetic force of this charged particles inside this conductor is given by F is equal to BQE sin theta. If theta is equal to 90 degree, it becomes F is equal to BQV. This is called equation 1. Now B means magnetic field, Q means charged particles, and V means velocity of the charged particles. Now velocity of the charged particles is given by, so we know the distance by time taken. Here distance is length is L, time is T. So if I substitute here, it becomes BQL by T. So it becomes what, children? F is equal to Q by T is nothing but I is equal to Q by T, current. So it becomes BIL sin theta. This is nothing but the expression for the force carrying conductor when it is kept in the magnetic field. Bil sin theta. Bil sin theta. If theta is equal to 90 degree, that is sin 90 is equal to 1, it becomes maximum. If theta is equal to 0, it becomes minimum. Okay, please note down this. So now later on, after understanding this, we'll understand that force carrying due to two parallel conductors, means two conductors. So we have considered one. Let us take two conductors. Let us take two conductors which is going to carry the amount of current. So this is the wire, means the force between two parallel carrying conductors, that we are going to get the expression. Now let us assume this is a wire 1, this is a wire 2, they are parallel to each other, and here dot I am going to take, here I am going to take into mark. Dot means what, children? The magnetic field is coming outside and it is moving inside. This is force 1, this is force 2, and this one you call as, that is B2, this is B1, okay, and they are separated by distance D. So this is, we are going to get the expression for force carrying due to, that is two parallel conductors going to be carried a current. Now dear children, very simple point. Now the magnetic field due to this one, I mean the magnetic field due to B2 and B1. This is first magnetic field, this is second magnetic field, and they are going to carry the current. So very important point, this is distance between the two parallel carrying conductors. So we know that according to the force carrying this conductor given by F is equal to B1, okay, and we know that I L sin theta. This is just we have derived F is equal to Bill sin theta. Now what is going to happen, children? The amount of magnetic field we should get. So this is formula for force acting on this. Now here this magnetic field is given by, here this magnetic field is given by B is equal to, that is we can write directly mu naught times of I divided by 2 pi d. Here I am going to take distance. So what I am doing, I have taken force which is acting on the wire, this one, from this that is B1IL sin theta. Okay, now here B1IL sin theta, and here current 2 is acting on this, and this is current 1. Okay, so then becomes children mu naught I1 2 pi d. So if I substitute this one here, it becomes what children? F is equal to mu naught by 2 pi into, I am going to substitute, that is B value substituted, I1 I2 into L. If theta is equal to 90 degree, we'll get, that is force acting on this length of the wire is equal to mu naught by 2 pi I1 I2 into L. This is the force carrying between two parallel conductors. If they are moving in the same direction, they are going to be attracted. If they are moving in the opposite direction, they are going to be repulsed. This is all about we understood in this class, that is straight wire means the magnetic field due to straight wire, circular loop, solenoid, toroid, force on carrying conductor, and also force carrying between the two parallel conductors. Okay, so next class we'll discuss about moving coil galvanometer. Okay, thank you children. If you understand, please share to who are preparing for CT exam. Thank you, and subscribe please.